Understanding physics, and I'm going to talk about the experiment to find Young's modulus. Thomas Young, one of the cleverest people who have ever lived. I've got an autobiography of him, The Last Man Who Knew Everything. We know him from Young's modulus. We know him from Young's double slit experiment. It's amazing. I might just do a video about what a clever git this fellow was. He was a very, very clever bloke. Anyway, shut up. Let's do it. So what we're going to do is we're going to stretch a copper wire, and we're going to do a graph of the load against the extension. Okay, so a length of wire, minimum 1 meter. If you've got a bench long enough, 2 meters, great. So one end of the wire is going to be held between 2 wooden blocks, and you wrap the wire around one of the blocks, and then you get a G clamp and you clamp it nice and tight to the end of the bench. The other end of the wire goes over a bench pulley, and then you make a loop, and you can hang masses, 100-gram masses, on that end of the wire. And we measure the extension with a little ruler. Talk a bit more about that in a minute. I suggest you use wire which is about 0.5 millimeter in diameter. That's SWG 26 for your technician, by the way. If it's any thicker than that, then you'll need a ridiculous amount of masses to actually make it stretch and to make it snap. I find that that's the good wire to use. That's the good diameter to use. About SWG 26. We're going to use a digital micrometer to measure the diameter of the wire. Okay, you can use an ordinary micrometer, but somebody will need to show you how to actually read the micrometer. It's not mega difficult, but if you use a digital one, you don't have to worry about that. To measure the extension, we're going to use a 15 centimeter ruler and a little bit of tape stuck on near the end of the wire. So this is our equipment. You might want a little handheld lens as well to try and read the extension as accurately as you can. So top tips. First of all, wrap the wire several times around one of the wooden blocks, and then grip it really, really tightly, because we don't want it to slip. Okay, we want the wire to stretch, not to be slipping out of the blocks. So that, make sure you've got a good secure connection there. This is how I measure the extension. I put a triangular piece of sticky label. Do you know the white labels, like address labels? And a piece of that, I cut it out and I stick it onto the end of the wire, about 20 centimeters from the end. Put a few 100 grams on the wire just to get it straight, and then I sellotape my ruler to the bench so that the tip of the triangle is on 0. And if you do that with a little bit of practice, then when you're reading off the ruler, you are reading the extension. Yes, because when it's not extending, it's on 0. So you sellotape a ruler to the table, and then use a handheld magnifier, like a magnifying glass, because you need to read at least to the nearest 0.5 millimeter. Yes. Take care when you're tying your mass holder, your 100-gram mass holder, to the wire, that you do a really, really good knot that isn't going to slip. The amount of times students have done this and it fails because basically they've done a rubbish knot. You know, there's going to be quite a lot of tension in the wire. Do a really, really good tight knot. Yes, so that doesn't slip. Measure the diameter of the wire in 3 different places and then take an average. It might be the case that there's some variation in the diameter of the wire. So you're supposed to do that, measure it in 3 different places and then take an average. And as I said, using a digital micrometer, it's much, much easier to read than a mechanical one. And what you do is you turn the spindle on the end until it starts to click. And when it's click, 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 that means it's tight. If you don't do that, then you might over tighten it and you could damage the micrometer. Your teacher should, or a technician should, show you how to use a micrometer properly. Okay. The longer the wire is, the bigger the extension. Now, most physics lab benches, you should be able to manage 1 meter of wire. If you can get it up to 2 meters, that would help, because then the extension would be twice as much. Yes. Before you start loading it up, yeah, after you've put a couple of 100 grams on, make sure you measure the length of the wire, maybe with a tape measure, like a metal tape measure, to the nearest millimeter. Measure the original length of the wire, because you'll need that in your calculation. It's a fiddly experiment. If you do have time to do a practice run, that would help. Okay, it is fiddly, this one. Safety, there's a few things I need to mention. Now, if you've got a wire with a lot of tension in it, then it's storing a lot of elastic potential energy. And when it snaps, you may get something called a whiplash effect. It snaps and it goes, whew. Yes. Now, a ductile material like copper shouldn't do that. If you were doing a steel wire, then there'd be a big danger of that happening. Okay. Nevertheless, the person loading the wire should be aware that when it snaps, it may come flying at them very, very quickly. So they should be aware of that, and they should wear safety specs as well. Another point is that when it snaps, it's going to have about 20, maybe even 30 100-gram masses, and these are going to fall to the floor. So I would protect the floor, maybe put somebody's nice fluffy coat on the floor or a bag. Certainly don't have it so it falls on anybody's toes, because that could be quite painful. Now, ideally, a graph of load, I'm plotting load in 100 grams, yes, against extension in millimeters, should look something like this. So you have your elastic region and then the plastic region up to the breaking point. The graph will look like this. It's really just the elastic region that we're interested in, because that's what we're going to use to find the Young's modulus. Yes. At the beginning of the graph, what you might find is that there's like a bit of a curve at the beginning. And that's probably just due to the fact that the wire isn't straight to begin with. You need a few masses on just to straighten the wire, and there'll be a little bit of slipping at your knot and where the wire is gripped at the other end. So maybe ignore the first 300 grams. Yeah, pretend they're not there. If you don't plot them on your graph, I mean, at the end of the day, if the graph is a straight line, then it shouldn't affect your overall result. But yeah, so there might be a little bit of a curve at the beginning, yes, which if you do a preliminary graph, you can take that into account. You could do a preliminary experiment. Now, to find out, what you could do is you could find out what load gets you to the limit of proportionality. And the limit of proportionality it's here. It's where the graph stops being a straight line. And to be honest, anything after that we're not interested in. Yes. So what you could do is a preliminary to find out what load you need to snap the wire. Do that graph, and then if you find, oh yes, it starts going plastic at about 15 newtons, then do a more accurate graph up to that load, and then use that graph to find your Young's modulus. This is how you work out the Young's modulus. So using at the limit of proportionality, so that's where the graph stops being a straight line. So Young's modulus is stress over strain. Stress is force over area. Strain is extension over original length. So it's FL over AX. F is the load in newtons at the limit of proportionality. So it's the mass in kilograms times 9.81. X is the extension at that point. L is the original length. Yes. A is the cross-sectional area of the wire. Now, when you've got your value of Young's modulus, what you should do is research a value. For example, off this website here, I got a value that said it's between 130 and 145 gigapascal. So you can compare your value with that value, maybe work out the percentage difference between them, and then you can comment on the accuracy of your value. Uncertainties, there's quite a few. Now, micrometers have got a resolution of 1/100th of a millimeter. Now, if you're using a wire which has a diameter of about 1/2 a millimeter, so you're talking about 2%, that's in measuring the diameter. So the uncertainty in the area, because it's pi r squared, will be 4%. Yeah. A 1 meter length of wire, now it's only going to stretch a few millimeters, maybe 5 millimeters at the elastic limit. When it actually starts going plastic, then it will stretch loads and loads and loads. It will stretch about 150 millimeters before it snaps. But at the elastic limit, you're only talking about 5 millimeters. And we're just measuring, even with our handheld lens, to a precision of about 1/2 a millimeter. So you're talking 10%. I would say that's probably the biggest uncertainty, is measuring the extension of the wire, about 10%. There's going to be some uncertainty now in the value of the load that causes plastic deformation. So as I said earlier, it's going to be plus or minus 200 grams. So out of 200 grams, you're talking about 10% there. So that's also significant as well. So the overall uncertainty, adding all of these together, is quite large. It's about 25%. Yes? There are more accurate ways of getting the Young's modulus. If you go on and do mechanical engineering at university, you will come across them. Yes? These are the things that are going to be ticked off, yeah, the skills, etc. Pretty straightforward, pretty obvious. Where it says we did several things to increase the accuracy, mention them in your report. For example, how you did everything as accurately as you could. You used a micrometer to get the diameter. You did it 3 times and took an average, etc. So make sure there's evidence in your report that your teacher can go tick, tick, tick. Yeah, they've done A, C, and E.